Now it is interesting to note, remember that I can implement the same thing with a full adder. Okay, so if you remember what was the implementation that we had with the full adder? Basically we had, you know, the sum and carry going out like this, right? This is my full adder. Okay, carry out coming downwards. Okay, remember my full adder cell is like this. Let me just recollect that. I'm giving the input A, B, my carry in is here, C out is here, and this is the sum. Okay, this is C out, right? That's the configuration. So if I look at this, I'm going to ground this input because this is the A bit, and then I'm going to connect this to a D flip flop, right? I have three such things. Okay, this is my flip flop. Okay, and you remember that all we had to do in a full adder was to take the output back to the A input, right? So for example, this is what we needed here. For B we needed this, and of course the carry has to propagate like this. This is the ripple adder, right? And the sum is being driven by the sum of the full adder is driving the flip flop input, right? And all we had to do to the other inputs was to connect it to 0, 0 and 1. So here what we are basically saying is the inputs are 0, 0, 1. That means I am adding to the full adder 1 every time, whatever the previous state is, right? If you look at this next state table, if you add 1 to each of these states, if you add 0, 0, 1, right, and do all the carry propagation, you will get the next state appropriately, right? And when you come to 1, 1, 1 and you add 1, because it's only a 3-bit adder, it will overflow. The last carry out will become 1, but we are ignoring that, and therefore it will just cycle back to 0, 0, 0, right? So this is the implementation that we had of the full adder based circuit. Okay, so again this is the clock, let's not forget that. Okay, and remember, only when there is a dot there is a connection, otherwise there is no connection, right? Now we need to analyze and see why we got two different implementations like this, or rather are these two implementations different in the first place, right? Right. So the interesting part is that you will see that these two implementations are basically one and the same. Okay, the reason for that is what is on your right hand side is actually a simplified logic diagram of the left hand side, but with a specific input of that 0, 0, 1. I'll show you what that is. Okay, so you take this full adder circuit. The full adder basically is, okay, I will deliberately draw this as A and B instead of a 3 input XOR. This is C in, and you get the sum out here, right? And the carry out is going to be what? The carry out is going to be, let's see, okay, the carry out is going to be AB okay. BC right. So you get AB here, you get AC here, BC here, and then you simply pass these three inputs to a 3 input OR gate and you will be done. This is my C out. Okay. So effectively what you have now got is the full adder's internal circuit diagram. So now let us analyze what happens to each of these full adders when the B input. So in what we have done is, to the full adder we have assigned the B input to a constant number, that is 0, 0, 1, okay, starting from MSB to LSB, right. So B2 is B2 equal to 0, B1 equal to 0, B0 equal to 1. So the first thing you note is, the moment you actually do B0 equal to 1, right, then what you get here effectively is, in this sum circuit, right, this will become an XOR of the A input 1 and remember that carry, the first full adder's carry, right, full adder 0, 1, 2, right, full adder 0's carry in is 0, so this is also 0. So if I simplify this particular circuit here, the output of this A XORed with 1 is just A bar, okay, because it has to be A B bar plus B A bar and B is 1, therefore you will get A bar here. Likewise, when you XOR something with 0, you get the same thing back, and therefore this is going to be A bar, right, and that is why you saw that this full adder maps to this inverter perfectly, right. Effectively the two XOR gates simplify down to an inverter, okay. Now let us look at the next case, okay. The next case, this of course the carry out now is coming from the previous full adder, and therefore you cannot simply ignore it, right, you cannot ignore it, you have to be careful about that, right. So and what is the sum that is actually coming out there? If you look at the sum of the full adder, it is simply going to be A bar, right, or it is going to be Y0 bar, right. What about the carry out? The carry out of this particular circuit, right. So when B equal to 1 and C in equal to 0, right, then okay, so I'll take this off. So when C in equal to 0, these two AND gates basically will give you a 0, and therefore it is going to be C out will simply be equal to A, and what is our A input? It is equal to Y0, right. So therefore in the next full adder 1, the carry in is Y0, A input is Y1, but B input is 0. So again you come back and evaluate this sequence of XOR gates here, okay, for full adder 1, okay. So what you get is carry in equals Y0, B input equals 0 and A input equals Y1, okay. Now this is again straightforward, go ahead and do that A XOR B XOR C operation using the two XOR gates. You have Y1 here, the A input, right, this is A, B is tied to 0, that means the output of this XOR gate is A, and the y naught is coming as carry in here, right? This is your C in, and therefore you will simply get A XOR C in as the answer here, right? If you tie B to 0 and if A equal to y1 and B equal to y naught, then this is equal to y naught XOR y1. Okay, so that is what you see here. Therefore, this full adder maps to this particular XOR gate perfectly again. Okay, there is nothing inconsistent between these two implementations, right? So now the third one becomes very interesting. So what happens to the C out of the full adder 1 in this case? Okay, so if you take the C out, B input is 0. That means you have an AB. So if you look at this implementation here, so let me just draw that again, right? I have an AB. I'm going to tie this to 0. I have two other AND gates. Not like this. Right, so this output is 0 because the B input is 0. Likewise, this output is also 0. That means what is going to come out of this OR gate, final OR gate, which is the carry out circuit of the full adder, is only going to be the output of this AND gate, which happens to be A into C in. So you will get A into and C in as the output carry out, right? And what is that? It is just y naught y1 equal to the C out. It is y naught into y1. Okay. So now what you do is we have to look at the final full adder, right, and understand why we have this complicated diagram here. Okay. So for full adder 2, A equals y2, right? Let's go back and see the A input is y2, the the A input is y2, B input is 0, the C in is actually just y naught and y1. Okay, so therefore you will see that I can now again go ahead and do that same A XOR B XOR C operation, right? So this is A, B is 0, that means I get back A here. Right, and C in is, so the output will just be A XOR C in. This is exactly like what happened in the previous full adder. We got exactly the same thing here, just that the input was different. The C in was y naught y1. Now C in was y naught in the previous case. Now it is going to be y naught y1. Therefore, if I look at this, it will be A XOR, what is A? It is y2 XOR y naught y1. And if I expand this, I will get y2 y naught y1 whole bar or y2 bar y naught y1, right, which is exactly what we saw as the implementation and the Boolean expression here, y2 and y naught y1 whole bar plus y2 bar y1 y naught, right? And therefore this expression for full adder 2 also is simplified significantly, right? Now let's just suppose we were to continue this expression to figure out what is the C out that, and suppose we had a 4-bit adder, what is the C out of this? So we can also evaluate that. Remember, B is 0, right? So AB plus BC, both of them are 0. You're just going to get A into C as the output carry out. So the C out of full adder 2 will be A and Cn. Again, that's exactly the same as what we got previously here. Simply because, and this is a result of the B input being 0, that's all, right? And therefore, I can just come here and say that my A and C in is going to be Y2, because A is Y2, into C in, which happens to be Y0, Y1. Okay. So, if you see what we are doing here, right, effectively the difference between the full adder based implementation and this this raw implementation here, which is using the logic gates directly, we are not rippling this carry. So if you remember, we said that when we wanted to do this full adder design, we said we'll go hierarchically, right? We we will evaluate bit by bit and propagate the carry out to the next stage and then go like that. That's the ripple adder that we made. But now what are we doing? We are actually considering the effect of the carry out of the previous stages 0 and 1 in stage 2 directly, right? And that's why we are getting all these expressions here, okay? And of course, this is conditioned on the fact that the B input is 0, 0, 1. Now, if you did something else, then you have to obviously account for that accordingly, right? On a related note, the non-hierarchical design of a full adder, where you actually don't ripple the carry through, but instead evaluate the carry and the sum as a function of all the previous carries, C ins and all the previous A and B, right, is exactly what a carry look ahead adder is, right? Exactly like this, you will get very similar, you will get very similar expressions, but now as a function of A0, B0, A1, B1, A2, B2 and so on. So the sum S0 will be a function of only A0 and B0. The sum S1 will be a function of A1, B1, A0, B0. Sum S2 will be a function of A2, B2, A1, B1 and A0, B0. You will not have this carry out rippling through. Instead, you will evaluate each carry multiple times by throwing in more hardware and make the whole addition process much faster in the process, right? So this is just to, I wanted to highlight the importance of making sure that two designs are equivalent, okay? And they indeed will come out to be so if you consider the hard-coded values that we have put into this full adder. Sometimes even a multiplier we might choose to do something like that. You must know how to reduce that to the consider the hard-coded inputs and reduce the logic diagram accordingly, right? So now, having set this kind of a counter, right? So I'll show you this. Right. So if you look at this particular thing, right, of course the carry out is now going through like this. This is the clock. Okay, so this is Y0, Y1, Y2, right? Now, with this setup, I can do very interesting things. I don't have to count only up by a factor of 1. I could even count up by a factor of 2 by simply doing this, right? If I am going to add 2 to this every single time, right, then I can simply increment my counter by a value of 2. Well, I could even change this to this in which case I will be incrementing by a factor of 3 every time I did this, right? So you can do the, so if you were to, let's just draw the state diagram directly here. You start with 0, 0, 0, and let's say I'm going to add only 2 to it, right? You'll get 0, 1, 0, 1, 0, 0, 1, 1, 0, and then back to 0, 0, 0, 0, right? So what happens is, if you choose to skip your counting in this way, right, then you will go through only a subset of the 8 states, right, or a subset of the 2 power n states that you actually have available. And of course you don't have to go through every single state when you are designing such counters, right? So this full adder based thing is a very good idea, where you simply start with this, and now in order to figure out what is the simplified logic diagram, you could go ahead and do the same thing that I told you earlier. Start with a full adder A XOR B XOR C, right? You know that the input here is 0, right? That, and therefore that has to just simply be A. So if you look at it, this output will simply be equal to A. So the implementation here will simply be feeding Y0 back to this thing, right? This equivalent circuit will be a flip-flop which is just fed back, which is, we have to check that actually. So let's see. So A is 0, B and C in is also 0. So you get Y0 XOR 0, which is Y0, and Y0, yeah. So you'll just get Y0 back, and therefore, yeah. So this is actually quite obvious. You see that this state actually is just a 0, right? You have nothing to do here, right? The output of that Y0 is simply 0. You don't have to, do anything or change that state, right? So all you have to do effectively is to do 2-bit counting and fix that other bit to 0, right? Likewise, I could also, if I can somehow reset this counter into 0, 0, 1 state as my starting state, then it would go to 0, 1, 1, 1, 0, 1, 1, 1, 1, okay. So it's going to go back in circles like this. Of course, the first bit will simply be fixed to 1. You don't have to do anything. You are still doing just 2-bit counting, and therefore only for the Y1 and Y0 you have to figure out the logic diagram appropriately and get this to work accordingly, right? So this is a very useful technique where you don't have to go around simplifying the Boolean expressions from scratch, solving the K-map each time. You can start with a full ripple adder and actually just simplify that diagram down to its lowest form and get the logic diagram implemented appropriately, right?